Good morning, everyone. Thank you for being here. I just come back in the early this morning from the conference, so forgive me if I'm kind of do the best. So I'm Jin Fu. I'm a faculty member in the department at IBM, and many of you probably know that our lab works on the role of cellular organelles in the lipid metabolism. Particularly, we care about the role of lysosome and lipid droplets in the lipid transport and signaling. So in our lab, our research heavily rely on the image-based analysis. So we can say our primary goal to analyze the organelles is including quantify the quantity of the organelle, that means numbers, sizes, and their spatial relationship. That means they're to stay together or separated from each other, and their cellular distribution, like how they distribute in the cells, in the periphery, or in the cell center, or some particular area. So today I'm going to use several examples to show you how we use the M4 facility, mainly focus on the confocal microscope and the CX7 cell mix in our research. So these two equipment is super important to our research, but they do have their pros and cons. We use them for the different purpose, but we do combine them every day to obtain the data for under the different purpose. So first, and I just said we quantify the organelles numbers. I believe most of you, if you use these two equipment, this will be very common and maybe popular purpose for everyone. So in our lab, here is an example for the image obtained from confocal microscope. You can say in each images it includes 3 or 4 cells. I didn't really label the boundary of the cells, but I believe you can see it very clearly. And you can see the bright puncta shown here is the lipid droplet. So we use the dipeptide, which specifically bind to the neutral lipids, which is the core of lipid droplet structure. So we can visualize the lipid droplets in the different conditions. And here shows we have wild type cells and different gene knockout cells, and we rescue this gene by introduce the gene back to the cells. And we look at how this kind of manipulation affect the lipid droplet numbers. You can say just by eyes, I believe you can appreciate that if you knock out the genes, then this lipid droplet numbers reduce a lot. And then you put this gene back, it can rescue this lipid droplet numbers. And then we want to know how much, right? You can just show 3 or 4 cells to say, okay, we found this. So we still need to do the quantification based on the confocal image. And here shows you can use the software, which is free software. I believe most of you already know that. ImageJ, or now we call it Fiji, to quantify the cellular lipid droplet. And here shows, first you can manually tell the software where the boundary of the cell, then you can define it. And here the yellow line shows that I just use my mouse and draw the boundary of these cells. And then of course you can set the threshold to tell the software, okay, I think which signal we think is real lipid droplet. Because you can see in the cells, there's some other kind of structure here, but they're not something we're interested in. I guess it probably ER, but you also can think in the background. We only care about this puncta, which is brighter than other signals. So we can use the threshold to label this puncta we're interested, which are already labeled as red. And then you tell software, okay, now quantify the punctas. Use a function called analyze particle or particle analysis. Then the software can tell you, like in these cells, how many puncta you have. Now we have 67 punctas. That means 67 lipid droplets we define. And the total area is this, and this area becomes like 1.4% of the entire cell area. So we know how many or how much lipid droplet in these cells. And the software also can tell us, like for each puncta, how big it is. Because the window I only show you 20 lipid droplet here, labeled from 1 to 20, but the area numbers, you can say some is big, some is small. So we can get this information. But still, if you're doing this way, let's say we're really working very hard. I put the student in front of the computer, work in a whole day, maximum 100 cells, I guess, because you need to draw the cell boundary for each cell. It's really slow and a lot of work. Then if we use CX7, we can quantify a lot of lung cells and just in 96 well plates. So here, it's still similar things, but the different project. You can see we use the cell mass first to define where the cells, which is different from the control image. We need to draw the boundary of cells manually. But here, when you spin the cells, so the software can recognize the boundary like the blue lines shown here, it defines each cells. And then still body page to spin the cells, you can see those bright punctures, that's the lipid droplet. Then similar as the image, we still need to tell software what kind of signal we define lipid droplet. But if you have used X and you probably know there are much more parameters you can adjust, like intensity, area, shape, everything. So you can tell software which signal you think is real lipid droplet. And after that, you can quantify. And here in this experiment, we show the different amount of cellular lipid droplet like this one. You have really pure lipid droplet. And then software can do the quantification for you, and the bar will show here. But the difference, please note that each dot is not only one cell, now it's one well, because we quantify the well level. And in each well, you can quantify thousands of cells. And then in one experiment, you can easily do the replication for 6 wells to 12 wells, or if you want, you can do dozen wells for one condition. So then for this experiment, we are quantify tons of thousands of cells. So it's completely different from control microscope. I think that this is one thing for CX7 for all years. And then we also analyze the organelles spatial relationship to say if they're fit together or separated or so here is the example. One of our projects is working on the interaction between lysosome and the lipid droplet. If you know about autophagy, you probably know autophagy. Lysosome also can screw autophagy pathway to eat lipid droplet. In that way, lipid droplet and lysosome will contact with each other. But it depends on the mechanism of autophagy. If they use the micro-autophagy, then lipid droplet surface will be bound by the autophagy membrane, which we can use LC3 and the marker. But this case is not what we are interested in. We kind of propose a new hypothesis to say lysosome and the lipid droplet can directly contact each other, which allows the lipid transfer from lysosome to lipid droplet. Then we will have problem. How can we distinguish our case from the autophagy? Then here I show you the control images, and here I still use the body page to spin lipid droplet, and also use LC3 to recognize the autophagosome. And the LAMP2 is a marker for lysosome. Here you can see for this lipid droplet, it is surrounded by LC3. That means this lipid droplet is already in autophagosome. And this one, this lipid droplet about to contact with this lysosome. So I think this is a very typical event of autophagy of lipid droplet, but this is not the event we're going to look at. And what we care about is something like this. You can see lysosome and the lipid droplet contact with each other, but this lipid droplet LC3 free. Here is LC3. This lipid droplet doesn't have LC3 bond. So this is not a typical autophagy pathway. However, you can think about that here. I just show you very small area of the cells. If you want to quantify this event in one cell, you need to look at each lysosome, each lipid droplet, and to really count how many events are there. Maybe you spend, I don't know, half an hour, you only quantify one cell. And don't think about like a lot of cells. So for this purpose, we still can do it in CX7. So still similarly, we can use body tape for lipid droplet, LAMP2 for lysosome, LC3 for autophagosome. I know the image is very small, you probably cannot really see that. but we can define which the ROI or the interest of regional interest that we're going to quantify. And here, the magenta, this mask highlights the overlay part of the lysosome lipid droplet, but without LC3. So when we see this color, we know, okay, this contact is no LC3 there. And this purple color just highlight LC3 and the lipid droplet. When we see the purple color, we know, okay, this lipid droplet will go to uphold. And in this way, we can quantify the event we care about. This contact but no LC3. You can see in the LDL treatment, you can see the difference and something. Okay, so by now I think you probably think, okay, CX7 is cool, you can do a lot of quantification, but then why we still need a control? It's not always the case. For example, we use a confocal microscope more to do the explorer research. We want to see clearly in details what exactly happens in the cell. Here is the example. This experiment performed by my postdoc, Dr. here. Yeah, this is really unexpected observation. Okay, so while we did this experiment, she used the LDL to treat the cell for 2 hours compared to the control, and then she used 2 different lipid droplet protein antibody against the lipid droplet protein to sting lipid droplet. One is ADRP, the other is TP47. These are 2 proteins on the surface of the lipid droplet. So basically, if you sting them, you will see the lipid droplet. And still, body pit is a dye I just talked about. So theoretically, these 3 signals should colocalize together always because they all sting the lipid droplet. But when we did this and used the confocal microscope to observe the slide, she found after the treatment, TP47 looks like increase a lot. You see a lot of TP47 signal compared to the control cells. However, ADRP things doesn't really change much. So this is something really interesting. We don't understand why TP47 responds to LDL treatment so dramatically, but ADRP doesn't. So we want to say if this something we saw is real, so we quantify the TP47, ADRP, and the body weight by Zelomic CX7. You can see, of course, after the treatment, the lipid droplet increased a lot. TP47, it did increase a lot. ADRP looks like it didn't really increase within 1 hour, but at 2 hours, it increased a little bit. So that's the thing. Something you cannot see by confocal. Maybe there's some difference if you quantify a lot of cells. So I think here it is. But this result kind of consistent with what we saw in the confocal microscope. That's TP47. That responds to LDL a lot. So what happens? Then here, still the same experiment. ADRP, TP47, and body weight. Here, I could just show you the image from LDL treatment. You can see here, I enlarged this image from this frame. The magenta color labeled ADRP, and the yellow color labeled TP47. You can see these 2 proteins, they not always colocalize together. It seems to us, for those bigger lipid droplets, it has more ADRP on it. That's these magenta colors. And the smaller lipid droplet, it has more TP47. So by enlarge the image to look at the detail, it looks like these 2 lipid droplet proteins have a preference to localize the different size of the lipid droplet. So this is our first impression. But so far, we're still working on that. Try to find out why and how, what that means. But this does some confocal microscope can tell us. Okay, the first example is we also working on the lysosome conditioning in our research. So you may not really familiar what's a lysosome conditioning. Here, I show you 3 cells under different conditions, and those red puncta represent the lysosome, 1.1 lysosome. this is the Y-type cells. In the normal situation, you can see the lysosome just spread out throughout the entire cells. It's just everywhere. When we knock out these genes, lysosome cluster to the perinuclear area. The cellular distribution has been changed. And then when they overexpress these proteins, you can see more lysosome just go to the cell periphery, they go to the cell tips and accumulate there. So that means lysosome positioning can really be regulated by a range of genes, actually a lot, over 50 genes can regulate the lysosome positioning. And in natural condition, lysosome positioning responds to different cellular environment stimuli, including pH, nutrients. Actually, nutrient is the most studied conditions. When cell have a lot of nutrient, the lysosome just prefer to spread out the entire cells. When cell is starved, lysosome cluster to the cell center in most cases, I would say. And this also related to some disease. For example, the cancer cells, they have more peripheral lysosome. But for those cells, for the neurodegenerative cell from neurodegenerative disease, those lysosomes prefer to cluster to the cell periphery. So why lysosome do that and what's the function actually, we really don't know. That's why we're really interested about that. So first, if we want to study that, we need to have a method to quantitatively analyze the lysosome position. Here, I show you a method that we use. I believe some other lab may also did some similar things. But as here, still we use cell mask to sting the cell to define the cell boundary. Once we know this blue line will show the cell boundary. Once we know the cell boundary, we can make another mask. Yeah, ROI. Like the green line shows here, we just shrink the cell boundary a little bit. Of course, this distance we can define and your interest. Here we define like 15. And then the area between this blue and the green lines, we define the cell groups. Okay. And we can use the MQC. We can use the TGN marker, TGN36. This is a protein localized on transguard network. And you probably know that TGN mainly localized at the microtubule organized center. When we say lysosome cluster and the cell perinuclear area, that's the lysosome cluster MQC. And by studying these proteins, we know where is MQC. And here, the red line just defines this area. Here's the red line, the TGN36. And then in this red area, we define it's like cell center, or you can call it the perinuclear. Okay, then any other area between this green line and the red line, we define the intermediate area. So in this way, we can divide the cell into 3 areas: peripheral area, intermediate area, and the cell center. Of course, if you want, you can even divide it into more sections. And then after we spin the lysosome, we can see where's the lysosome localized. And here, the cyan color, also my mouse, the cyan color here highlights the lysosome localized on the peripheral area. And the red color here highlights the lysosome localized in the cell center area. And then we can do the quantification, like how many lysosomes in different sections, how much area that, how much percentage of the lysosome encountered in the entire population, and then we can do the computation. And here is a project in our lab. We try to figure out how lysosome positioning responds to different amino acids. And the undergraduate student, Brad, did this experiment. He treated the cells with different individual amino acids and to see how lysosome positioning responds to this. Okay, I will stop here. I hope by this for example, you get some idea about how we use these tools in our lab research. I want to thank my postdoc, Dr. Huai Zheng, and the student Brad for their contribution to this slide. Of course, Sharina and Lee helped me a lot about the problem. Thank you.
My project, like our project in our labs, we are trying to find out the synergistic effect of glucose and cadmium on the insulin resistance in hepatocellular carcinoma cells. So for that, we choose two cell lines, HG2 and HO7, which are very common hepatocellular carcinoma cell lines. And we expose them for a long period of time, like for 6 months with low dose of cadmium and glucose, just to check whether like heavy metal has some impact on insulin resistance or not. So like we have a lot of different experiments, but since we are just going to focus on the CX7 technology, so I just choose one experiment here, which is the glucose uptake. And this assay, like experiment, is very necessary to find out whether a cell is insulin resistant or not. Because if a cell is insulin resistant and if you will give it insulin, sorry, the glucose, it will not respond to the insulin and there will be less uptake like of glucose into the cells as compared to the control cells. So for that, like we have here 6 conditions, but I didn't know that like to put all the data, just so that's why I choose only 2 conditions. So it's the control and this is the treated cells, which are treated with the cadmium and high glucose for a period of 6 months. And you can see like a glucose intake within the control, like within the treated cells, it's significantly lower as compared to the control cells. And how we did this, like we tried to optimize, we did it like to optimize this assay. We did it with the help of the 12-DG, which is an analog of glucose. So whenever like once 12-DG goes inside the cells, so usually in the glycolysis cycle there are several enzymes like glucose 6-phosphatase and several. But whenever 12-DG goes inside the cells, G6PC works with this, and after that, none of the enzyme will work with the 12-DG and it can activate with the cells, and it will excite like with a particular filters. Like it will excite at 485 and emission will be like around 545. So you can see the staining here. This is the nuclear staining, 12-DG, which is the glucotic staining. This is the composite image. And how did we calculate the intensity? So for that, we were masking the glucose, and so we were masking the nucleus here, and from the nucleus we were taking for like it's dependent upon the cell area side. So we were just checking the intensity of channel 2. Like we were trying to capture the whole cell's intensity of channel 2. So you can see it was significantly like a lower as compared to the control.
Today, I'm going to talk about my research. My research showed that high expressed glucose study by giving the 750 working numbers in the to conduct this research, I asked a few questions, and today I would like to share how I use the standard currency for that questions. So I have 4 questions for this project. So first thing is, does high extracellular glucose means the uncertainty? And second, does high extracellular glucose increase the activity? And question 3 is, how will we use optimization of phosphorus and the last question is, is charity a kind of large society? So today you can talk about. Thank you. So today I'm going to share not only CX7 but also other genetic program I research. First, the first question was whether high extracellular glucose induced campus contractility. So this contractility means I use flexibility in the negative component that I was using. More contractility that will result the higher displacement of the microception. And this leading to the smaller size of the protein. So to measure the area of these chain proteins, So I used the CX7 system and perform the following analysis for that. My purpose of the analysis was to quantify the area of the pattern to reach only single cell variability. So I use localization algorithm for that. First, the pattern expressing fluorescence was set as ROI, and then the pattern with multi-cell attachment combining through nuclear number quantification was excluded from the analysis. Cross-country, the area of ROI pattern to reach one cell was measured. So, as a result, I confirmed that breast cancer cells contractility was increased with higher glucose levels. And next, for the second question, I employed the same equipment to assess the increase of stress fiber caused by glucose. For this analysis, I used the target activation algorithm. Firstly, cell segmentation was performed using copy signal, and a specific region was defined as a ROI based on the nucleus. Subsequently, the intensity and area of the stress fibers within the ROI were analyzed. The laboratory results show increased intensity of F14 in single cell level with high glucose. And the figure on the right displays chemical microscopy imaging of the cells used for quantitative analysis. And my third question was whether glucose increased the formation of ectomyosin, which induces cell contractility. Ectomyosin refers to a thin myosin complex that formed within the cytoplasm. Ectomyosin contractility occurs when the phosphorylated myosin protein is on the active amines. Therefore, I performed co-localization to confirm that the glucose increased the co-localization of phosphorylated myosin protein and active amines. Confocal microscope images were obtained using CX7 replication objective, and intensity spectra from phosphoproteins were acquired using -5 from the image. The degree of localization was quantified by Pearson correlation value of the two protein intensities. So as a result, it was confirmed that high glucose induced the formation of ectomyosin by increasing the localization of two proteins. This is my last question. My last question was whether difference in extracellular glucose concentration alters metabolic activity. To address this question, I analyzed the glycolysis and state phosphorylation rate following glucose treatment using a cross analyzer. As changes in metabolic activity after glucose treatment can appear rapidly, so I injected glucose into the cell using droplet. The findings revealed that high glucose treatment increased glycolysis while decreasing oxidation. So, in response to the question arising from my study, I obtained unbiased and diverse data by pricing this to customers' document. I conclude my presentation by expressing my experiences in my degree for their support and assistance in this project.